All right. Hello and welcome everyone. Can you guys hear me? This is a mic check. If anyone can confirm that you can hear me, then we can move on to the sessions. Can you just react with emojis if my voice is audible enough? All right. Okay. And also, if you can see my screen, I'm screen sharing on the slides. Okay. So we're gonna start off by quickly revising, um, or rather picking up from the last session that you guys had with Yab and Obed on Friday. I believe you guys have seen how you can write control structures in MeTTa. So that's where we're going to pick up from. Okay, so as you all are familiar with, in MeTTa we have the control structure, which is if, which also acts as a function. So in MeTTa we use functional evaluation, and which makes the if function evaluate to some true or false value depending on the argument's evaluation result. So as you can see here, the syntax is fairly simple. We have kind of what looks like the math if expression, where you have a condition that needs to be satisfied. Then based on that condition, there's some piece of code that's going to execute. So the way this works is, if the condition here is reduced to true, then this part, or the immediately first part, gets reduced or executed. So if you write true here, then true will be returned, or if you write another expression right here that needs to be further reduced, the execution goes to this branch. So we have basically two branches. When the expression passed to if is true, the first branch gets reduced, and in the else case, the next expression gets reduced or executed. Let's see how this works with a simple example. Here I have a function check age that takes an argument age value and compares it with the number 18. As you can see over here, we have an if structure. So the if structure's first argument is the Boolean condition that is to be evaluated or reduced. So I have this greater than or equal age 18 written over here. So as I've said earlier, if the condition of the Boolean passed to the if function reduces to true, the first branch gets executed or returned, and on the opposite case, the next expression gets reduced or returned. So that's how this function works over here. So if I pass a number 20, then my expected output would be adult, since the first value is going to be returned due to this Boolean expression being true. That is, 20 is greater than or equal to 18.
Okay. Someone question.
Okay, Sheila.
I would like to understand what level of students are in this breakout room. Is it a continuation from students who have previously joined, or are they new? I just want to understand what level they are.
Yeah, okay, I actually haven't checked. Can you guys react by raising your hands if you're in the continuation group, if you want to revise the previous resources that we've seen so far, or the ones that want to proceed? Quickly show of hands if you're in the first group, which means you want to revise the source materials that we've seen so far. Is this thing still on?
Yes. Guys, please don't be shy. This will help us help you. Does it mean everyone is in for continuation from Friday? Okay, cool. Thank you.
Okay, so we can continue. So yeah, as you can see, this is how the basic expression works, how the if function works. I'm just gonna write a couple of examples and show you guys some helpful tips when you write if expressions. So one thing that we need to see is the negation operation. I'm not sure if you guys have seen about this, but I'm going to go over it. And also we have Boolean operators, or and so we're going to see these and how we apply those. So the negation operation is basically a not function. So it's a function that takes a single argument, which is going to be an expression or truth value, a Boolean, and returns its negation. So if I have not false, the output I'm going to get is going to be true, and vice versa. Not true is going to reduce to false. And also, obviously, the OR operator is going to also be a function that takes a single argument. I'm sorry, two arguments. It's a binary function. So true or false is going to be true. The only case this reduces to false is if both arguments are false. And same goes for the AND operator. It's going to be a binary function. It's going to take true or false arguments and return the reduced value. So when you write if expressions in the negation forms or using the operators, the way we typically do it is a bit different. So in languages like C++ or C# or Java, we have the not operator being the exclamation mark. We don't use this exclamation mark to negate expressions. So what we typically do is enclose the expression within a not expression. So if I have some kind of Boolean expression here, then I say lesser and I return greater. If I have some example expression like this and I want to reduce it, when it's run, the output is going to be greater, since I'm negating this expression right here. 5 is greater than 4, that is true. Then when it's negated, it becomes false, essentially reducing to this outcome over here. So you can use the remaining Boolean operators also in the same manner in conjunction with the if expression. Alright, so I'm moving to the next part, the main part of today's session, which is going to be loops and recursion. So how do we write loops in a functional programming language like MeTTa? So since the domain of this programming language is not imperative, we do not have keywords like for or while to basically iterate over a list of items or to repeatedly do some kinds of operations. Instead, the mechanism we use is recursion, meaning we iterate over expressions or do things repeatedly using recursion. So the concept behind this is quite simple. Since everything is basically seen as a function, and we do not have the for and while loops that we are used to in other imperative programming languages, we use recursively going over expressions or doing things by calling the function itself. So a recursive function by definition is a function that calls itself. So the way we achieve this iteration is by calling the function itself until we reach some kind of breaking point and exit that loop, which is the end condition. So that's what recursion basically is, and we're going to see how we can kind of engineer this construct in MeTTa. Okay, so there are two main golden rules that we need to follow in writing recursive functions. The first rule is to have a base case. What's the base case? So a base case is it's basically a condition that halts or stops the recursion, or you can view it as an exit door, where you have a function calling itself repeatedly for n number of times. Then when it gets to the exit door, it basically exits that recursive call to itself and returns some kind of value. So it's going to stop calling itself. So that's the base case. The second golden rule is the recursive step. So this is the rule where by which we define how the smaller calls to the function, or how the original problem is broken down into smaller pieces, is determined. This is where we determine how we break down the function calls into sub problems and then do the same thing until we reach the base case. So this is going to be the recursive step, or the relationship we define between the variables in order to progress to the base case based on the operations that we perform in the recursive function. So this is basically the part where the function calls itself. Okay, so I need you to focus on the fact that every recursive function needs to have both rules to avoid infinite loops. If you have one lacking, then the function is going to keep on calling itself, which results in an infinite loop, and eventually the program is going to crash and it's going to mess up. Okay, let's see some examples related to writing recursive functions in MeTTa. So the first example is a countdown function, where we have a number passed to a function then we print numbers recursively, minimizing it by 1. So a basic definition of a countdown, where you have, for instance, if you have 10, if you pass 10, then the output will be 10, then 9, then 8, then 7, and so on. So this is how the function would look like. So over here we have an if condition, which says if n is less than 0, then if n is less than or equal to 0, then we're going to return 0, which is clearly our our base case, where the function halts from calling itself, where it stops from calling itself and returns a value, as I mentioned earlier, and the value is 0 over here. Then in the else branch over here, we have a let expression where we print the n value, and over here we have an interesting line of code, which is the recursive step. That is where the function calls itself, and the recursive relationship over here is that we pass n minimized by 1 to the function itself in order to progress to the next step. So as you can imagine, this function calls itself right here. If n was, say, 3, when it comes to this comparison, this reduces to false, effectively jumping to this expression. Then we print it out, we print the value out, we get 3, and we subtract 1 from it and pass it to the countdown function again. So we pass it as 2. Now the value of n is going to be 2, and the same comparison occurs over here, which reduces to false. Again, this condition is not met, it's going to reduce to false. It comes down here and prints n again. It's going to be 2 this time, and the function is called once more again, and the value it's being called on is 1. The condition fails again. It comes here, it subtracts 1, which makes it 0, and since this condition is satisfied, we return 0, and the values 3 to 1 are logged to the screen, or we see them output on our console. This is the first one. The second example is the famous factorial function. I'm sure everyone is familiar with the factorial function, where you have n factorial being the product of the consecutive numbers subtracted by 1 each. So you have n times n minus 1 times n minus 2 times up to 1. So how do we write this factorial function using recursion? It's quite simple. As you can see over here, our base case. So first thing we need to think about is our base case. When does our program halt? This is the first question that needs to come to mind. So the first question is, where does it halt? And we have it here, and it's going to be when n reaches 0. What do we do when n reaches 0? We basically return 1, which is this value right here. And the next thing we think about is the recursive call, which is the relationship we have over here, and that's going to be n times factorial of n minus 1. So this is the recursive relationship, and yeah, so this is how we write the factorial function. We can check it out by running it on our code editor quickly. I'm just gonna copy it here, and let's see. by running factorial of 4, and as you can see we have 24, and factorial of 3, for instance, it's going to be 6. So yeah, this is how we basically iterate over and work out the factorial of a given number. So okay, yeah, we're gonna see another example right here, but let me just pause for a minute, and I'm gonna give you guys the chance to ask a couple of questions if something is not clear. I can so that I can go over it again and maybe explain it in another way, so you guys can feel free and ask me. So does anyone have any questions they want to ask?
Sir, in the first sum you got, I don't understand the let things.
um, Sorry, I didn't hear your voice very clearly. Could you please repeat it again?
Yeah, in the example one, the let keyword is there.
Oh, okay, this one.
Yeah, that's what I can't understand.
Okay, cool. So what's happening down here is we have the let expression being used over here. Let me just code it on the VS Code, and I can explain it there as I go. Okay, so we have the function countdown. We have argument n, and the condition we have is if n is less than or equal to 1, I think. Oh, it's 0. Then we return 0. In the else case is what the control structure of let is happening. So what we want to do is to print out values as we count down from n downwards until we get to basically 0. So what we did is, so this right here, it's a way of discarding the output of whatever is being reduced. It's basically equivalent to the underscore operator in Python, where you have, for instance, we want to decouple some coordinate values like 1, 2, and we don't need this x value. Then we have a way of basically ignoring this value. This is the equivalent of doing the same thing in Python. So since we are printing to the console, we do not need the output of this being kept on a variable or something. So that's why we did this over here. So we basically print ln the value, or it's like basically saying print in Python. Then comes the recursive relationship, which is countdown. Then what do we pass to the next recursive call of the function is the question that is being asked over here. So we basically minimize or subtract n by 1 and pass it to the countdown or the next iterative call. So we basically say minus n1. So this is what's happening right here. this is what's happening. So yeah, if we see output of this by running it starting from let me just copy and comment that part. As you can see, we have 5 4 3 2 1 being logged to the console. The structure we used here is just to temporarily hold that value before decrementing it and print it to the console. Is it clear now? I can do it again if it's not very much clear.
Yeah, sir, it's clear.
Okay, cool. Anyone else have questions? All right. Let's move on to the next function that we are going to write recursively. So you can see the mathematical formula written down over here, where we have to calculate the sum of numbers up to n. So this is basically returning the sum of n and the sum of the numbers previous to it. So if we have 5 passed to the function, it's going to be 5 plus 4 plus 3 plus 2 plus 1 plus 0. It's like the factorial function, only the only way it's different is the multiplicative operator. It's replaced with addition right here, and it's going to run up to 0. So how do we code this sum function and iterate over the values up to n and return the sum? Let's see how we can do that. So over here, first thing that we need to ask while writing recursive functions, as I've mentioned earlier, is to think of the base case. What's going to be the base case of the function, or the halting condition of the function? So we start from n, and that value is going to be the value that's going to be passed on or to the next recursive calls of the function. So one thing that I need to focus on is, what does that value need to be in order for the function execution to stop? In this case, it's going to be 0. So if the value of n is less than or equals to 0, then I halt and return some value, and that value is going to be 0. So that takes care of the base case for me. The next main question is the recursive step. So how do I recurse, or how do I need to call the function in order to reach the base case? What's the relationship? So the relationship is laid down over here. We have n plus sum of n minus 1. This is going to be our recursive relationship. So I simply come here and write that in this else case. So it's going to be n plus, this is our operator plus, and sum2 is the function that we need to call, and the state change is to basically modify n by subtracting 1 from it. So this is what we did over here. So it's n minus 1. Now we're passing, if n is 5, for instance, right here, it's going to be 4. Then it's going to compute the same thing going into the function call. It's going to come here, and n minus 1 is going to be 3. It's going to enter again to another sum function. The difference is going to be 2, 1, then it finally reaches 0, and when it reaches 0, it's going to return 0. And the sums are going to be computed and returned, which is going to be 15. Does anyone have any questions? Maybe any kind of ambiguity that we need to address? Feel free to ask. All right. Thank you. Let's move on. So the next important concept is the accumulator concept. So while recursing over functions, we sometimes need to update values and carry those updated values to the next step. The accumulator is a kind of way of updating where you kind of store values. Think of it like a backpack where you carry down certain values that you want to keep while recursing. It's not going to be an invariant. It's going to vary from one recursion call to the next recursion call. Say if you want to collect some kind of values together, then the state is going to change. So that's basically what an accumulator is. So there's an analogy over here, and it's basically to think of it like a backpack. You carry down the recursive steps and you store the intermediate results as you go on it. And when you reach the base case, what you return is the accumulator. So say you've accumulated some values based on some kind of computation. Those computations are being stored as intermediate values, and finally when you reach the base case, you return that accumulator value. So that's how the accumulator works. Yeah, so we also have an example down here where we have to write multiplication by addition. It's better to see how we use the accumulator to kind of propagate intermediate values to the end. Yeah, okay, so the problem description says write a function, and we have the function structure right here, multiplied by addition, and it takes two values, a and b, that multiplies two numbers using only addition and recursion. So we have also a hint down here, add a to itself b times. The goal is to practice carrying a value through recursive calls. Yeah, what we are basically doing is adding a to itself b times and propagating that added value using the accumulator. So let me quickly switch to the code editor, and we're gonna see how we're gonna code this. Okay, so let's call it mult_add, and we have a and b as our arguments. We want to add a b times, and we're going to also have our accumulator being passed as an argument. Alright, so what's going to be our base case? What's the base case? Since we are trying to do this to replace a times b by basically adding a how many times? B times, let's say AB. So how do you see the recursive relationship terminating is the first question we need to ask. So while writing recursive functions, it's best to identify the things that vary, what varies between recursive calls, and the other thing is the invariant, what stays constant. These need to be answered. So obviously from here we can identify that the property that doesn't vary is a, the value a. Since we add it a couple of times, we don't need to change it, so it's going to be an invariant. And the thing that varies, or the property that varies, is going to be first b, since we basically subtract 1 from it to model a way of passing the minimized value of it to the next function call, which is going to be b minus 1. This is what we're basically going to do. And also we have our accumulator. Our accumulator is also going to change, and this is going to be ACC plus A. This is very simple. Since we have a previous accumulator, then we take that accumulator value and add A to it and replace the previous one with the new accumulator value. This is what we're going to do. Now that we've addressed these main questions, let's go back to the base case. So what's going to be the base case? The base case is going to be if b equals to 0, which means if b becomes 0, if b progresses to the value of 0, then we return 0. This is the base case. Let me paste it back here. Okay, now that we've gotten that taken care of, let's think of the recursive case. So now this is the place where we determine how we call the function itself. So it's going to be where we call the function b ACC. So this is where these three questions that we've answered earlier, these two questions we've answered earlier are going to help us. So we know that b is going to change across recursive calls, which means we have b being decremented by 1 on every recursive call, and also we know that the accumulator is going to change, and the way it changes is plus, not 1 but ACC, and what amount do we add to it? A amount is to be added to it. So this basically solves our recursive case. Now let's check if this works. Let's say we want to multiply 4 by 5, and what's going to be our starting point for our accumulator is going to be 0. since the multiplicative identity is 0. Okay, let's see what the output looks like. Oddly, I'm getting 0 because I made a mistake right here. I mentioned earlier that we need to return the accumulator over here. That's why it returned 0. Okay, so as you can see, it's working properly now. I have a multiplication operator written recursively using addition. Does anyone have any questions or any types of ambiguities that I need to clear? Feel free to ask, you guys. Do you guys have any questions? Okay. Okay. I see it's clear. Also, I think you guys have gone through these concepts in your classes and other programming languages as well, so it's only a matter of rearranging the syntax. It shouldn't be that difficult, but in any case, there must not be any kinds of ambiguities or things that are not clear to you. Feel free to ask even the slightest questions. Okay, so I'm going to move on. So we have another example down here. So the second example is for us to create an energy loop. What was the energy loop? It's basically the task is basically to create a function. This is the structure of the function. Workday is going to take a single argument, energy, that simulates a daily routine. So the logic is, if energy is greater than 0, it's going to print working, and it's going to call workday and basically call the next step of the execution. But if the energy reaches 0, then it's going to return time to sleep. I hope this is very clear. The goal of this exercise is to combine print ln, if, and recursion into a single function. So we're going to need to print ln some stuff to the console. We're going to need to write if expressions and also recurse using the logics that we've seen so far. Okay, so first thing we need to answer is, what's the variant and what's the invariant in the function? We have energy. Clearly energy is going to be a variant, so it's going to change from one recursion step to the next recursion step. We don't have an invariant in this case. So what's the base case? The base case is going to be if the energy reaches 0. If the energy reaches 0, that's going to be the base case, where we need to return time to sleep. And the recursive case is going to be decrementing the energy by a value of 1. This is quite straightforward. Yeah, so this is how the function looks down here. We have workday defined, and its argument is energy, and the condition we're going to check is if energy is greater than 0. Then if it is greater than 0, when we need to print working using the println function. And in the third argument of the let expression, we perform the recursive call, which is calling workday on a value decremented by 1. This is the recursive case. The base case is going to be time to sleep when it reaches 0. So yeah, this is very straightforward. You guys can try to write it out and test if you really understand how this works on by yourself. But we're gonna move on to the next topics that we have, and after seeing those, we're gonna have a quick exercise for you guys to kind of get your hands in the mud and try to write the code. Okay, so let's summarize the concepts that we have seen so far. This is a comparison table for MeTTa versus imperative programming, specifically for Python or C++ imperative programming languages. Yeah, so firstly we have the decision. How does decision work in an imperative programming language? We have if statements where we have this kind of structure. If some kind of condition is true, then we follow on to execute a body of code or block of code. But in MeTTa or functional programming language paradigm, we have if not as a statement but as a function, which makes it an expression. So it reduces to some kind of value. So we have if some Boolean condition happens, then the left is going to be returned if the condition is true, and the right side of the expression is going to be returned if it's false. This is how we write decision logics in imperative compared to functional programming languages. Doing repetitions, we have for loops for I in range n. We repeat some kind of block of code, but in functional programming languages we have to write it recursively using the same function calling itself. How it ends, how we end repeated calling. The loop is going to finish executing, whereas in functional programming languages we have the base case being reached. So this is the quick summary. Does anyone have any questions? You can write on the chat or raise your hands to ask. Feel free to. And let's move on to the next step, and that is the common pitfalls while writing recursive functions, the things that we need to avoid by writing recursive functions. Okay, the first and obvious one is missing or incorrect base case. Guys, if you miss this, the function is going to enter an infinite loop and it's not going to exit until it finishes the resources allotted to it. So basically your program is going to crash. So missing this is very, very bad in your programs when writing programs in a larger scale. So you guys need to keep an eye out for this. So let's see this as an example. So here's a basic definition of a Fibonacci sequence function.
லேப்டாப் இதுலயே அட்டெண்ட் பண்ணிக்கிறியா? இதுல ஜாயின் பண்ண முடியும். அதான் சொல்றேன், இதுலயே அட்டெண்ட் பண்ணிக்கிறேன். ஆமா, அதுலயே அட்டெண்ட். அந்த டைம்ல கேட்டுட்டு இருக்கேன். முடிச்சுட்டு நான் லேப்டாப்
Did you guys have any questions? I'm guessing they left their mics on. Okay, so this is the definition for the Fibonacci sequence generator function. Yeah, so here we see that we have the base case defined as when n equals to 1, we return 1. And the recursive relationship we have down here is fib of n minus 1 plus fib of n minus 2. But let me take you to a specific scenario. Say n equals 2. When n equals 2, obviously you see that fib of 0 is being called over here, which automatically skips this check. So it's going to continue on, moving on to the next recursive calls, which are negative numbers, and it's going to continue on calling itself until the resource allotted to it is no more. So it enters an infinite loop. That's what happens when n equals to 0. So can anyone tell me the missing base case over here? It's quite simple. What's the base case that I'm missing right here? That's going to complete the function definition. Any volunteers? It's n equals to 0, right? That's what we need to complete the base case. And we're going to string them using the OR operator. So what we basically do here is add n equals 1 or n equals 0 so that it returns 1 in both cases. So keep an eye out for this, for not missing the base case. Okay, the other one is the other most important thing that you need to keep an eye out for is the wrong recurrence relation pitfall. So what kind of pitfall is this one? So earlier we've seen that if we fail to correctly specify the base case, we're going to enter an infinite loop. This is more of a recursive step logic error. So it's going to be concerned with the way we call the next step of the function. Specifically, asking the question ourselves by saying, does this recursive call lead me eventually to the base case? So down here we have this function is going to compute the number of people in a queue standing where a person is standing. Say if a person is standing at the 5th queue, then if he wants to know how many number of people are standing behind him, then it's going to be starting from 1 and adding the number of people until he's reached at the front. So if he's at the 5th place, it's going to be 1 plus 1 plus 1 plus 1, which is going to be 4. So yeah, there's a logic error down here in how the recursive relationship is defined. So what we typically need to do down here is to decrement n by 1 in order to reach 1. But what this function definition is doing is going in the opposite direction. It's going to add values and increment it, so it doesn't reach the base case. So the wrong recurrence relation is going to also affect the program execution, and you need to keep an eye out for that also. The other thing, the other most important thing is forgetting to return values. In recursive functions, it's totally important for you guys to remember that every recursive function needs to return a value. Every recursive function needs to return some kind of value. So we're going to see the sum2 function that we've seen earlier. We have the base case written down here, and we have the recursive case properly defined down here, where we have n plus sum of n minus 1. But what's being returned in the recursive case? So println res is being reduced down here. This is going to be reduced into empty parentheses, which is not a value, which is going to mess up our program execution. So println prints any value it's given, but it returns empty parentheses. So this is not correct. What we typically need to do is to return this sum, which is res, in order to properly fix this function and not mess it up. Okay. So yeah, these are the common pitfalls that we need to avoid while writing recursive functions in MeTTa. And again, if you guys have any questions regarding the pitfalls, I'm willing to explain, and we can even write down the codes and see the outcomes if you want. Yeah, I'm gonna give you guys the chance to ask any questions that you have so that we can clear them before moving on to the challenges for today. Okay. I'm taking the silence as you guys having no questions, which is great. And yeah, so let's move on to the challenges we have. We're gonna have 2 challenges, and we're gonna go through them and see how we can approach them, and you guys can try to write the code for them. Yeah, okay. So the first challenge is to simulate a daily savings plan where we have n number of days, amount, which is going to be saving per day, and we're going to have an accumulator, the running total in the jar that we are going to put our savings per day. So the task is to return the total saved after n days using an accumulator. So how do we approach this problem? Let's go to the code editor, and I'm going to quickly write this. So first question that we need to ask ourselves is the variant. The variant. What's going to be the variant? First thing is the number of days, right? The next variant we have is the accumulator. Where we have the running sum of the accumulated value which is going to be our jar basically. Earlier we've said that our accumulator is kind of a backpack where we put intermediate values onto. So our accumulator is going to be a variant. The next one is the invariant. Do we have an invariant down here? Yeah, right? We have the amount. The amount is going to be an invariant, which means going from recursive call to the to the other recursive call, it's not going to change. So yeah, now we can write our function. It's going to have how many arguments, sorry. It's going to have 3, right? N number of days, amount, and the accumulator. And we're gonna have an if expression. If some condition occurs, which is going to be our base case, we return our accumulator. Otherwise we call savings on so n is going to vary, new n. Amount is not going to vary, it's going to stay the same, and we're going to also have new accumulator over here. So yeah, now that we have had this structure defined, I want you guys to try and fill in the gaps and try to solve the remaining part of the puzzle. Can you guys do that? I believe you guys have your PCs with you, right? Can I get a confirmation? All right, sweet. Okay, try to fill in the gaps and tell me if something's not working for you. These are placeholders. They're going to be expressions to update the accumulator in the n value. Okay, let's start from the recursive calls. Okay, yes, if n equals 0, this is going to be our base case, right? So let's write it down here. N equals 0, and the recursive step is going to be basically minimizing n by 1, right? Since it's going to progress towards this value. And also we're going to have the accumulator changing by ACC plus amount. Okay, so savings, let's say 10, and the amount we want to save is 70 rupees or dollars each day, and the unit case for addition is going to be 0. And when we see, it's going to be 700. Fun fact, you can also do this function definition using multiplication. we use this example to simply show you how we can recurse over values. Yeah, so we can use this to check if our answer is correct. Then 70 times 10 is 700. Our output is 700, which means we're good to go. Our function is working properly. Great. Okay, now let's move on to the next challenge. This next one is where we have this cute robot over here. It's going to climb up a set of stairs, and what we asked to do is, as the robot climbs a flight of stairs, we're gonna recalibrate every 3 steps so that it pauses. So on step 1, 2, 3, when it reaches to 3, it's going to pause and then move on again. 1, 4, 5, 6. It's the next 3 step. It's gonna pause again. 1, 2, 3. It's going to be 9. It's gonna pause again. That's what we're going to do. So the function structure looks like this. Climb, we have total number of steps, the current step that we're on, that the robot is currently on, and the number of pauses. So we're asked to return the number of pauses given the total number of steps a flight of stairs has. So if it has 6 stairs in front of it, how many times is it going to pause? 2 times, right? Over here, then over here at the last step. So at the end, after recursing, we're going to return 2. If it's 9, we're going to return 3. So, and so on. If the current step is a multiple of 3, increment the pauses accumulator, and the goal is to return the total number of pauses. And we have a hint down here, and the hint is to use the modulo operator. Yeah, so let's take a couple of minutes, and so that you guys can try to attempt this challenge, and you can maybe send the answer on the chat, or you can raise any questions that you have, any difficulties running the code. You can ask me, and I'm going to be available. First, you guys need to try it out, and we're going to solve it together with me. Yeah, let's give you guys 5 minutes to, I think 5 minutes is going to be enough, unless someone has already. The message is not quite clear. Could you speak through the mic and maybe explain what you're trying to do with this? Yeah. Okay. Yeah, that's how you write the modulo of the total number of steps. Yeah, but this is not complete, since what you need to return is the number of pauses it's going to take in order to completely climb up the number of steps. For example, if there are 9 steps, as we've seen earlier, it's going to take 3 pauses, right? 1, 2, pause, 4, 5, pause, 7, 8, pause. So we have 3 pauses total. Then we return those 3 values, which is going to be the accumulator basically. Also, the aim is to write it using recursion, since we're trying to practice writing recursive functions. Yes, yes, you're right. Your answer is right. It's correct. It's one way of doing it, right? That's the interesting part of programming. There are more than one ways to solve a problem, but specifically to this scenario, you're asked to write the solution using recursion. All right, cool. All right. Time's up, you guys. Uh, okay. Can you guys tell me what you've managed to code up? Okay. Let's just move on and see how we're gonna solve this. Okay, let's comment out this line. And okay, so what was the function? Let's call it number of steps, number of pauses instead. Okay. Oh, we already have a function definition. That's cool. Okay. And the first argument is going to be total total steps. Current step is the next argument, and the last argument is going to be pauses. Okay, let's do the same thing again. What varies? The variant and invariant. Yeah, let's answer these questions. So we have the total number of steps and the current step which the robot is going to update its state upon. So obviously this is going to be a variant. Current step is going to be a variant. It's going to change at every step. Also the pauses, since it's an accumulator always changes. The invariant in this case is going to be total steps. And what's going to be our base case? So imagine the robot is first, it's going to be on the ground. It being on the ground would mean its value for the current step is going to be 0. Then it's going to move up a level, then another level, another level, effectively updating the current step value. So the current step is also going to change. We've already determined that, but it eventually is going to reach the final step, which is going to be the total number of steps. So that's when the robot is going to stop climbing, which means our program is going to stop climbing when the current step eventually reaches the total number of steps, which we can formalize like this: total steps equals current step. Then if this condition is true, we can safely return what? The number of pauses it has endured so far. So what's going to be the recursive step? During the recursive step, let's just simply write total steps. So we already know that the total steps are not going to change, and the current step is definitely going to change. It's going to increment by current step plus 1. It's going to increment by 1, and the number of pauses is going to increment by 1. But this is not quite done yet, because we don't just increment pauses in every recursive case. We need an if condition to tell if the current step is a multiple of 3. We have that written down over here. So we need to do that. We obviously need to do that. So I'm going to come over here and I'm going to write another if condition. That condition is going to be the modulo operator, current step by 3, and this needs to be an equality outside. If this equals 0, then the way that I update the pauses value is going to change. is going to be different. I have total steps, it's going to be the same. Current steps step is also going to change by 1. It needs to change by 1, and also pauses needs to change by 1, by a value of 1. So this is the first condition. If this Boolean expression is true, then I'm gonna update my pauses value. But what if what does happen in the second step? Pauses are not going to change. Only the current step value is going to be updated. So now we have a completed function definition. We can test this by writing different test cases. Let's write total number of steps as 9. The current step is going to be at 0, since it's going to start from the ground level, which is effectively step number 0. And the number of pauses, which is going to be 0 also. And let's add a couple of other test cases, 3 and 6 and 3. So we expect this one to return how many pauses? 3 pauses. This one to return 2 pauses, and this one to return only a single pause. Let's see what the output looks like. Wonderful. As you can see, we have 3, 2, 1, which means our function is working properly, and we've successfully solved this challenge. So now, does anyone have any question? I can go over the whole function definition starting from the first steps. So you can really ask any questions that you have regarding this challenge. So launch away. If you have any questions, feel free. So here's the function. If you wanna maybe write it down on your code editor and compare. Let me copy it properly. I'm gonna also send the definition to the previous one. Guys, if there's even the slightest ambiguity that I need to clear up, you can definitely feel free to ask whatever you have in mind. Is it clear, Mr. Padmanabhan? I'm sorry if I butchered your name. I don't know how to pronounce it. I mean, I would call out some people by name if I could, but yeah, I don't know how to pronounce your names. Yeah, so is everything clear? All right. Everyone else?
Yes, sir. It's clear.
Okay, thank you, man. Did you guys get the same output as I showed in this code? All right, cool, man, cool. Okay. So, guys, we have a couple of minutes left in the session. So I'm just gonna quickly go through kind of a recap, a summary. If you guys don't have any questions to ask, if there's any questions, again, anyone can ask. Feel free to. Yeah. So today we've seen about two things mainly: how we write control flow using the if function. We've quickly recapped on that since you guys left off on this topic on Friday. We've gone through that and we've seen how we write the if function as an expression in MeTTa, and we've seen that we can how we can use the different Boolean operators to kind of perform Boolean operations on Boolean expressions by writing them in if expressions. Yeah, so we've also seen how we can write recursive functions to basically iterate over and over and kind of bring the idea of repetition from the imperative side of the paradigm to the functional side of things. So we've seen how we can write recursive functions. We've seen how we define base cases and recursive steps, the two golden rules of writing a recursive function. We've seen that a recursive function is a function that calls itself. Yeah, we've seen a couple of examples also. We've seen how we can write recursive cases in different use case scenarios. We've seen also another additional example. We've also seen the logic of the accumulator and how it works, how it works to carry down recursive step values to basically capture intermediate values of states. And yeah, we've gone through a couple of exercises and we've seen some common pitfalls to watch out for by writing recursive functions, and we've solved two challenges regarding recursion. I hope you guys have gained some kind of understanding from this lecture. If you've got any other questions, feel free to ask on the help desk. We're going to be available there anytime. You can go on there and write your questions, or if there's some kind of bug that's that has not been fixed for you, you can reach out and ask us. Yeah, so I hope you guys go on to practice the ideas of recursion and how to write recursive functions in MeTTa furthermore. Yeah, so guys, the way you become better in programming is by doing the things that you learn by yourself. So watching me code the solutions to the challenges might give you the illusion of you understanding the problem entirely and being able to code it by yourself. But it's entirely different when you see someone solve a problem and when you sit down and attempt to solve the problem by yourself. So what I urge you to do is take on some other examples, take on some recursive function definitions that you already know in other functions, then try to define them in MeTTa. You can first write them in Python or JavaScript or TypeScript, whatever language you prefer. Then you can map that logic to MeTTa and see how you've understood. You can write recursive functions. And yeah, that's all for today. Yeah, I'm looking forward to see you guys in the next session on Wednesday. It's going to be on Wednesday. So see you guys on Wednesday.